Hello everyone and welcome back to the second part of our discussion on the industrial stoichiometry for nitrogen industries. On the previous part of the video, we discussed the solution to the material balances of the Haber process or the production of ammonia. That process included a recycle and a purge stream. If you haven't watched that, I'm linking that to the description below. In this video, we will be focusing on the production of nitric acid through the Ostwald process. Shown here is a simplified diagram of the Ostwald process. It contains three basic steps: the oxidation step, performed in the oxidation chamber, the conversion step, performed in the converter, and the absorption step, performed in the absorption column. We will be discussing each of the steps separately, and we will also be solving examples for each of the steps. The overview of the process is our feed is pure ammonia, which goes through the oxidation chamber. The purpose of the oxidation chamber is to burn or oxidize ammonia. The purpose of the oxidation chamber is to convert or burn ammonia to produce nitrogen dioxide. And we can do that with the provision of air. So A1 here is air. And for engineering calculations, we are assuming that air consists of oxygen and nitrogen in the ratio of 21:79 per mole basis. If you will notice, we are no longer including the contribution of argon in the composition of air because we don't have any recycle streams in this process. Argon is usually included in the calculations if there is a recycle stream because there is a danger of accumulating too much argon in the system, as in the case of the Haber process. After the oxidation chamber, the OG here stands for oxidation gases. That is the effluent of the oxidation chamber, and that goes into the converter, wherein the main goal is to convert the produced nitrogen monoxide to nitrogen dioxide. There is also some nitrogen dioxide produced in the oxidation chamber, but it is usually at a very low amount. And we need to use a converter to make sure that the nitrogen dioxide is in appreciable levels in the converter gas. The converter gas is the effluent of the converter. Now, you might have noticed that there is an A2 in the process. A2 is what we call the secondary air. This is a provision of fresh air for the converter, and the purpose of this is to enhance the oxygen content of the mixture. This is in case that the oxygen gets depleted from the primary air A1. And finally, in the absorption column, the goal is to absorb nitrogen dioxide to turn that into nitric acid. Our product here is nitric acid solution, that is nitric acid and water. Our absorbent here, W, is usually pure water. And the absorber gases contain whatever substances are not dissolved in the water. Let us take a look at the steps individually. First, for the oxidation chamber. Again, the feed here is usually ammonia because ammonia is easier to combust than pure elemental nitrogen. A1 is what we call the primary air, consisting of oxygen and nitrogen. The nitrogen gas in this case is an inert in the process. We are assuming that it does not participate in the reaction itself. In the real world, nitrogen coming from the air reacts up to some extent with the oxygen also found in the air. That is through the oxidation of nitrogen to form various nitrogen oxides. However, it happens at a very small rate, and the produced nitrous oxides are at a very low concentrations that, for design purposes, we can initially assume that they are negligible. In the oxidation chamber, the main reaction that happens is the ammonia from the feed reacts with oxygen from the air to form nitrogen oxide and water. This is a simple combustion reaction that proceeds to form the most favorable product, and that is nitrogen monoxide. Balancing the equation, that would be multiply ammonia by 2, multiply water by 3, nitrogen monoxide is multiplied by 2, and the oxygen gas is multiplied by 5/2. You can use this equation, or we can use the equation with all of the coefficients as whole numbers. That would be 4 NH3 plus 5 O2 yields 4 NO plus 6 H2O. With the knowledge of this primary reaction, we can then deduce that our oxidation gases, or OG, consists of the products NO and H2O plus the unreacted reactant, ammonia, and oxygen, plus, of course, nitrogen, which is inert in this case. In some cases, we can simplify the analysis by assuming that ammonia is completely combusted in the oxidation chamber. If that happens, we simply don't have ammonia in the oxidation gases. In the next step, the oxidation gases enter the converter. The converter here is a catalytic reactor in which its main purpose is to convert nitrogen monoxide to nitrogen dioxide. The main reaction is nitrogen monoxide plus oxygen yields nitrogen dioxide. Balance, multiply 1/2 to oxygen. We can also write this as 2NO plus O2 yields 2NO2. As we have established earlier, our oxidation gases or OG typically consists of NO, H2O, ammonia if there is excess ammonia or uncombusted ammonia, and there's also oxygen and nitrogen. According to our primary chemical reaction in the converter, we can then deduce that our converter gases or CG consists of the primary products NO2, the unreacted reactants NO, H2O, O2, and N2, and also ammonia if there is still some left. Now, you would notice in our primary chemical reaction is that the only reactants are NO and O2. We already have oxygen in our feed stream to the converter, and that is coming from the effluent of the oxidation gases. However, in some instances, the oxygen present or the oxygen left in the oxidation gases is no longer enough to sustain the conversion from NO to NO2. If that happens, we would provide an additional stream of air. We call that A2 or secondary air. The secondary air still contains oxygen and nitrogen. However, for calculations purposes, the stream A2 is kept separate from stream A1. So we would have different balances for those two streams of air. Always keep in mind that the secondary air can be omitted in the Ostwald process. It really depends on the concentration of oxygen in the oxidation gases prior to entering the converter. If it is already enough, then there is no need for the secondary air. Finally, let's proceed to the last step of the process. The absorption column consists of 4 streams, that is 2 inlet streams and 2 outlet streams. The first inlet stream is CG or converter gases. Earlier, we have pointed out that this consists of NO2, NO, H2O, O2, N2, and if there is still some ammonia left over. Our other inlet stream in this case is our absorbents or water. Usually, pure water is used to absorb the NO2 in the converter gases. So, for calculations purposes, we would say that our absorbent is 100% water. Our first outlet stream is our product stream. This typically contains nitric acid and water. However, if ammonia is still present in your converter gases, ammonia has a high affinity with water. As such, it would also be absorbed by water. So we would have some traces of ammonia in the product stream here. This extra complication to the process can be eliminated if our initial assumption stands, and that is all of the ammonia was converted in the oxidation chamber. So for now, let us cross out ammonia in our list of substances. Finally, for our absorber gas, we can deduce what are its components by determining what is the main reaction happening in the absorption column. For the absorption process, we take nitrogen dioxide or NO2, combine it with water, and then we form the nitric acid, plus a byproduct NO. The byproduct NO or nitrogen monoxide can be recycled back to the converter in order for it to be turned back again to nitrogen dioxide. To balance the equation, we multiply NO2 by 3 and nitric acid by 2. Now that we know the primary chemical reaction happening in the absorption column, we can now deduce what are the components in the absorber gas. We still have our NO because this is part of the converter gas products and it is also a byproduct of the absorption reaction. We can also say that the absorption column contains the oxygen and nitrogen. because these are sparingly soluble in water and they are largely not absorbed. Also, if the absorption is not 100% efficient, there could be some lingering nitrogen dioxide in your absorber gas. Although in most of our calculations, a simplifying assumption is that the absorption is 100% efficient. And as such, there is no need for NO2 to be part of our absorber gas. Now, what about the water vapor from the converter gases? Remember that in the converter gases, water exists as a vapor because this is a byproduct of the oxidation or the combustion of ammonia. That's why it's still a vapor in this case. After absorption, the water vapor joins with the liquid water absorbent and it exits still as liquid water in the products. Now, water vapor can still be part of the absorber gases if we consider the humidity of the system. That is because liquid water exerts a vapor pressure, and that vapor pressure can be converted to the amount of water vapor present in the system. If you will neglect the humidity of the system, then we can say that the absorber gases do not contain water, for simplicity purposes. All of the basic assumptions will be discussed as we solve examples relating to the Ostwald process. Let's begin with our first example concerning the oxidation chamber. The problem states 100 kilograms per hour of pure ammonia is injected to the oxidation chamber along with 20% excess dry air. Determine the Orsat analysis and volumetric flow rate of the outlet gas if it exits at 1,400 degrees Celsius and 2.5 atmospheres. Our diagram in this case to represent our given is simply the oxidation chamber with the feed, typically ammonia, and with the primary air A1 and the product oxidation gases. Our feed is 100 kilograms per hour of pure ammonia, and our primary air is supplied at 20% excess. For our calculations purposes, we are stating that the air only consists of oxygen and nitrogen gases. We want to determine the Orsat analysis and the volumetric flow rate of the outlet gases, that is the oxidation gases. Our oxidation gases, in this case, would contain nitrogen monoxide, oxygen, and nitrogen. And of course, water is also a component of the oxidation gases, although we will not be including that in the Orsat analysis. You would notice that I did not include ammonia in the oxidation gases. That is because our main assumption here is that the ammonia is completely combusted. Now you might ask, when can you assume that ammonia is completely combusted? In this case, we were not given any value for the conversion of ammonia. And without the value of conversion or without the full analysis of the oxidation gases, there is no way for us to determine if ammonia was truly completely combusted. So let's assume complete combustion or oxidation. And with that, we can now label our unknown substances. O2 is N1, N2 is N2, NO is N3, oxygen in the effluent is N4, nitrogen in the effluent is still N2. Remember that nitrogen here is an inert, so whatever nitrogen gas enters in the air is also the nitrogen gas exiting in the oxidation gases. This is also true because in our main reaction here, nitrogen gas is not being produced. And finally, water is N5. Our approach here is relatively straightforward. We simply have to figure out what does 20% excess air means, and then we can proceed to our elemental balances. For us to be able to utilize the 20% excess air, we first have to determine what is the theoretical amount of oxygen needed. And for that, I will write again our balanced chemical equation, that is ammonia plus oxygen yields NO plus H2O. This balanced equation is important in determining the theoretical amount of oxygen needed. To solve for the NO2 theo, or the theoretical moles of oxygen needed for complete combustion, we start with 100 kilograms per hour of ammonia in the feed. If my basis is 1 hour operation, then we can say that the feed is 100 kilograms of ammonia. we simply convert this to moles, and that is 1 kilomole or kilogram mole of ammonia is equivalent to 17 kilograms of ammonia. This is simply the molecular weight of ammonia. Now, looking at the balanced equation, our conversion factor would be for every 4 kilomoles of ammonia, we are using 5 kilomoles of O2 or oxygen gas. Solving for NO2 Theo, this is 100 divided by 17 times 5 divided by 4. Our theoretical oxygen is 7.35 kilomoles. We can now apply the definition of percent excess air to determine how much oxygen was fed to the process. To refresh your memory, percent excess air is equal to the number of moles of oxygen fed minus the number of moles of oxygen theoretical, this is the 7.35 we have determined earlier, divided by the theoretical amount of oxygen. If this percent excess is 0.2 or 20%, we can directly solve for the amount of oxygen fed. That would be 0.2 multiplied to the NO2 Theo, 7.35, plus 7.35. The amount of oxygen fed to the process, NO2 fed, is equal to 8.82 kilomoles O2. And of course, since our basis is 1 hour of operation, when you want to convert this to a flow rate, this becomes 8.82 kilomoles per hour. From this amount of the oxygen fed, we can also deduce how much nitrogen was fed to the process, and that is simply by applying the ratio of 79/21 to this value of the NO2 fed. This pertains to 79 moles of nitrogen is present for every 21 moles of oxygen in the air. Multiplying, we get 33.18. This is the amount of nitrogen fed to the system. And just like that, we were able to solve for the values of N1 and N2. So let me clean this first and then we'll proceed to our elemental balances. For the elemental balances, let's start with the nitrogen balance. From our feed, we just have to convert 100 kilograms to 100 kilomoles, and that is by dividing with the molecular weight. So we say that 100 over 17, this is the number of kilomoles of nitrogen in the feed. Of course, we multiply this by 1 because there is only 1 nitrogen in ammonia. To this, we add the nitrogen coming from air, that is N2. This becomes 2 times 33.18. And this is equal to all of the nitrogen present in our oxidation gases. First, from nitrogen monoxide, we write this as N3 because there is only 1 mole of nitrogen in nitrogen monoxide, plus 2N2, 33.18. This is the free nitrogen found in the oxidation gases. As you can see here, this just cancels because they are equal on both sides of the equation, and we can now say that N3, or the number of moles of nitrogen monoxide in the system, is simply 100 divided by 17. That is 5.88 kilomoles NO. Next, we can perform the hydrogen balance. In our feed, we have 3 moles of hydrogen coming from ammonia. So we write that as 100 kilograms of ammonia divided by 17 kilograms per kilomole multiplied by 3, we get the number of kilomoles of hydrogen in the feed. And since there is no hydrogen in our air, this is now equal to the hydrogen in the oxidation gases, only coming from water. So we write this as 2 times N5 because there are 2 moles of hydrogen in water. From this, we can solve for N5. 100 divided by 17, which is 5.88. We multiply that with 3, and then we divide this with 2. N5 is 8.82. This is kilomoles H2O. Our last balance is the oxygen balance. Since there is no oxygen in the feed, let us go straight to the air. That is 2 times N1, 2 times 8.82 kilomoles of oxygen is equal to all of the oxygen present in the oxidation gases. That is coming from NO, 5.88, coming from O2, that is 2 times N4, and then coming from water, that is 8.82. Solving for N4, we have 2 times 8.82 minus 5.88 minus 8.82, and this is all divided by 2. Our N4 is 1.47 kilomole of O2. This is the amount of oxygen left in the oxidation gases after the process. Now that we have completed the composition of the oxidation gases, we can now proceed to answer the question. For the ORSAT analysis, we simply have to solve for the mole fractions of the components of the oxidation gases excluding water. So that would just be NO, O2, and N2. For that, we construct a simple table. We have the components NO, O2, and N2. We list their number of moles. This is in kilomoles. For NO, we have 5.88. For O2, 1.47. And for N2, 33.18. We get the total number of moles. That is 40.53 kilomoles. And then we can solve for their percent by mole. This is in ORSAT. ORSAT simply means excluding water. So for NO, that is 5.88 divided by 40.53. That is 14.51%. So you get the gist, and we simply repeat this for oxygen and nitrogen. For oxygen, that's 3.63%. And finally, for nitrogen, we have 81.87%. The total of the percent by moles is a little bit more than 100. That's because we were rounding off for all of the mole fractions. No? That is okay if the excess is a very small amount. It just comes from rounding off error. Now for the next question, we are being asked to solve for the volumetric flow rate of the outlet gases. Now, keep in mind that when we say outlet gases, this now includes water in the oxidation gases. We only excluded water for the purposes of the ORSAT analysis. But for the determination of the volumetric flow rate, we have to now include water. Now that we have laid out the solution to this problem, you can try to solve for the volumetric flow rate of the oxidation gases or the outlet gases. I will leave that to you as a practice problem. Let's proceed to the next example. This pertains to the converter. Without feeding secondary air to the converter, what is the maximum possible conversion of NO to NO2 from the previous example? So we will be continuing our problem solving with the results of the previous problem. Let us draw our diagram for the converter. The input to the converter is the output of the oxidation chamber, and that is the oxidation gases. And the output of the converter is called the converter gases. In the previous problem, we have established that our oxidation gases consists of NO, O2, N2, and H2O. We also determined the number of moles of these substances. For NO, that is 5.88 kilomoles. For O2, 1.47 kilomole. For nitrogen, that is 33.18 kilomoles. And finally, for water, 8.82 kilomoles. For the converter, we have our primary chemical reaction, that is NO plus O2 yields NO2 to to balance, we add 1/2 to the oxygen. Now, you have noticed that in this converter, we are not incorporating the secondary air. That's because we simply want the reaction to run with the remaining oxygen in the oxidation gases. Let's see how far that will go. In the converter gases, we expect the following to be present. Of course, we are expecting our products, NO2, to be present, and some of the excess components. Of course, we will have excess NO. We will also have excess nitrogen and excess H2O. You would have noticed that I did not include oxygen in the list of the converter gases. You can check in this case that oxygen is the limiting reactant, and as such, oxygen is the first reactant to be fully consumed. So we would expect that there is no oxygen in the converter gases. Labeling our unknowns, NO2 is N1, NO, N2, nitrogen gas is N3, and water is N4. Now, just coming from our preliminary assessment of the converter process, nitrogen gas or diatomic nitrogen is not involved in the reaction. As such, it's considered as an inert. That is also the case for water. So therefore, we would expect that the amount of nitrogen and the amount of oxygen is constant in this conversion process. What will only change is the amount of NO2 and NO in the converter gases. Let's proceed with the elemental balances. Let's start with the nitrogen balance. For this balance, let's start with the feed, the oxidation gases. From nitrogen monoxide, we have 5.88 plus the nitrogen coming in, that is 2 times 33.18. This is equal to, from nitrogen dioxide, N1, from nitrogen monoxide in the product, that is N2, and then we also have N3, that is 2 times 33.18. We can simply cancel the contribution of the inert nitrogen gas. Thus, we have our first equation, N1 plus N2 is equal to 5.88. We would need another equation to solve the values of N1 and N2. And that second equation, of course, would come from the oxygen balance. Our oxygen balance is written as 2 times 1.47 plus coming from the nitrogen monoxide, 5.88, and then coming from water, that is 8.82. On the product side, we have 2N1 plus N2 plus the contribution of water, still 8.82. We simply cancel that from both sides of the equation since water is an inert in this case. Simplifying, we have our second equation, 2N1 plus N2 is equal to 5.88 plus 2 times 1.47, equation 2. In this system of linear equations, we are assuming that N1 is our x, N2 is our y, and everything on the right-hand side of the equation is our collection of constants. Let's solve for N1 and N2. For our coefficients, for the first equation, that is 1, 1, and 5.88. For the second equation, the coefficients are 2, 1, and 5.88 plus 2 times 1.47. Solving, our N1 is 2.94 kilomoles of NO2, and our N2 is equal to also 2.94 kilomoles of NO. With this information, we can now represent the complete analysis of our converter gases. That is, NO2 is 2.94 kilomoles. NO is also 2.94 kilomoles. Our nitrogen gas is 33.18 kilomoles. And our water is 8.82 kilomoles. Now we are done with the analysis. Now let's answer the question. What is the maximum possible conversion of NO to NO2 in this converter? To answer that, let's review the definition of conversion. We define this as the number of moles reacted divided by the number of moles fed. Now, the numerator and denominator in this case pertains to the limiting reactant unless otherwise specified in the problem. In the problem, we are solving for the conversion from NO to NO2. Therefore, the mole reacted and mole fed both pertain to NO, or nitrogen monoxide. Another way of framing this equation for conversion is that the moles reacted is simply the difference between the number of moles of NO in the product and in the feed. So we say that this is NO in oxidation gases minus the NO in converter gases divided by the NO in oxidation gases. So this is fed minus output over fed. Substituting, we have NO in oxidation gases, or the feed, is 5.88 minus the NO in the outlet stream is 2.94 divided by the input, 5.88. The conversion is exactly 50%. Our conclusion in this case is, if we will not supplement the converter with secondary air, in short, we will only be using the oxygen left by the oxidation process, we can only convert 50% of the NO to NO2. And that is not good. If we are to maximize our yield of nitric acid, we need to maximize our supply of NO2. That means that we have to maximize the performance of the converter. And for that to happen, we need to supplement secondary air. That is the rationale of the next problem. In this follow-up question, we are asking, what is the minimum amount of secondary air that should be supplied to ensure the complete conversion of NO to NO2 in the converter? I have here summarized our diagram for this problem. The only thing that we added is the secondary air, that is for the provision of additional air to ensure that oxygen is sufficient for the conversion process. If you take a look at the composition of the converter gases, you would notice that there is only NO2, N2, and H2O. There is no oxygen nor nitrogen monoxide in the converter gases because we are aiming for complete conversion. That means that all of the nitrogen monoxide will be consumed, and also we will only be providing enough air such that all of the oxygen will be consumed. You would also notice that nitrogen gas is represented differently from the secondary air to the converter gases. That's because they are no longer equal quantities. You have nitrogen gas coming from the oxidation gases. You also have nitrogen gas coming from the secondary air. And those are not equal quantities. When you add them, you get the nitrogen in the converter gases. So nitrogen and water are still inerts in this case. Let us start our solution with the definition of the conversion. The conversion in this case is 1, and this pertains to converting NO to NO2. If the conversion is 1, that means that all of the reactants in the feed is converted to products in the product stream. So we can say that the entire 5.88 kilomoles of NO is converted to NO2. If we apply stoichiometry coming from our balanced equation, we simply multiply this by 1:1. That is 1 kilomole of NO2 per kilomole of NO. And this is still equal to 5.88 kilomoles of NO2. Basically, we have found our N3, or our third unknown. And that's all we need before we can proceed with the elemental balances. Let's start with the nitrogen balance. We will proceed similarly as we did earlier. Coming from the feed, the oxidation gases, nitrogen is 5.88 coming from NO plus 2 times 33.18 coming from the nitrogen in the feed. Coming from the secondary air, that is plus 2 N2. And then on the feed side, we have N3, which is 5.88. This is the number of kilomoles of NO2 in the product stream, plus 2N4. Again, we have two unknowns, so let's label this as equation 1 and then look for another equation describing the system for us to have two equations and two unknowns. Our second equation would come from the oxygen balance. Our oxygen balance is 5.88 coming from NO of the feed plus 2 times 1.47 coming from the remnant oxygen in the oxidation gases, plus coming from H2O, 8.82. From this, we add the oxygen coming from the air, that is 2N1. And this is equal to all of the oxygen in the converter gases. On the product side, we have 2 times N3, or 2 times 5.88, plus the oxygen coming from water, that's simply 8.82. The contribution of water in our oxygen balance can be cancelled because it's equal and because water is an inert in this process. From our oxygen balance, we can now solve for N1, which is the amount of oxygen fed to the process. That is 2 times 5.88 on the product side. And we subtract the terms from the left-hand side, that is minus 5.88 minus 2 times 1.47. All over 2. Our N1 is 1.47. This is kilomoles oxygen. Our interpretation for this is we need 1.47 kilomoles of oxygen more as an input to the process to ensure that we have complete combustion. But this is all theoretical calculations. In practice, we need to have some degree of percent excess oxygen or percent excess air to really ensure a high conversion from NO to NO2. The 1.47 kilomoles of oxygen here simply serves as our theoretical amount needed to complete the conversion. To answer the question, we can simply state that we need 1.47 kilomoles of oxygen in our secondary air, or to be more exact, we can solve for the amount of secondary air needed. That is simply A2 is equal to 1.47 kilomoles oxygen, and we multiply this by the ratio 100 over 21. The reasoning for this ratio is that for every 100 moles of air, there are 21 moles of oxygen. This offers us a conversion from moles of oxygen to moles of air. Our secondary air is 7 kilomoles air. And that is the backbone of the solution for problems involving the converter of an Ostwald process. Let's now consider the last part of the process, the absorption column. This is a continuation of the previous two problems. If maximum possible conversion is achieved in the converter, and the converter gas is fed countercurrently with 50 kilograms per hour of water as an absorbent, determine the composition of the absorber gas and the product. Assume that no water and nitric acid is present in the absorber gas. Here we have our diagram for the problem. So you would notice that we have the converter gas composition from the previous problem. If you continued to solve equation number 1 in the previous example, then that would yield the following values here. We have NO2, nitrogen gas, and water. Another input to our absorption column is the absorbent, that is water, flowing at 50 kilograms per hour. This is given in terms of mass, so we just have to convert this to moles so that we can incorporate this to our mole balances. In terms of our output streams, we have two. We have the absorber gas and the product. The product stream contains the nitric acid produced during the absorption process, along with some excess water introduced from the absorbent. The absorber gas contains nitrogen gas only and nitrogen monoxide. The nitrogen gas comes from the nitrogen in the converter gases. The nitrogen gas in this case is an inert. It does not participate in the reaction. So we can say that if there is 38.71 kilomoles of nitrogen gas in the converter gas, there is also 38.71 kilomoles of that in the absorber gas. That is especially true because nitrogen is just very sparingly soluble in water. So its absorption can be considered as negligible. The second component in our absorber gas is nitrogen monoxide. Where does this come from? This comes from the absorption reaction. If you will remember, our complete reaction is nitrogen dioxide plus water gives us nitric acid and nitrogen monoxide. The nitrogen monoxide is a byproduct in this case, And if we assume that nitrogen monoxide is only sparingly soluble in water, we can assume that all of the NO generated just comes out at the absorber gases. And with that, we can now begin with the elemental balances. Let's begin with the nitrogen balance. We have 5.88, this is in the converter gases, plus 2 times 38.71. There is no nitrogen in the absorbent stream, so we will go straight to the absorber gas stream. This would be 2 times 38.71 for nitrogen gas, plus N2 representing the nitrogen monoxide in the absorber gas stream. And to this, we add the nitrogen source from the product, that is the nitric acid. We simply add N3. From this equation, we can cancel the contribution of the nitrogen gas because it's just equal on both sides of the equation. And we have our simplified equation, N2 plus N3 is equal to 5.88. This is our equation 1. We need another equation with the variables N2 and N3 to determine their values. Let's have our next balance, the hydrogen balance. Starting with the converter gas, our only source of hydrogen is water. So that is 2 times 8.82 plus the hydrogen coming from the absorbents, which is water. That's 50 kilograms of water. We simply divide 50 with the molecular weight of water, that is 18 kilograms per kilomole, and this becomes the kilomoles of water. We multiply this by 2 because there are 2 moles of hydrogen per mole of water. And this is equal to all of the hydrogen in the outlet streams. There is no hydrogen in the absorber gas, and we only have our hydrogen in the product. So this becomes N3 plus 2 N4. This is equation number 2. Now we have 3 unknowns, that's N2, N3, and N4. In this case, we cannot perform the oxygen balance and call that our third equation because the systems of equation that would result when doing that would not give us a valuable solution. It would result to an infinitely many solutions. So with that limitation, we have to come up with another equation that describes our system. And we can do that by applying stoichiometry. Earlier, if you remember, I mentioned that we are assuming 100% conversion from NO2 to nitric acid. Or that's also saying that we are assuming that we have 100% absorption of the nitrogen dioxide gas. That means that we can perform stoichiometry to determine how much nitric acid was formed in the absorption process. For that, let's first balance our chemical equation. So we multiply NO2 by 3 and nitric acid by 2 to make it a balanced equation. Stoichiometry has taught us that we can relate the amount of NO2 in the converter gases to the amount of nitric acid in the product. So we can say that N3, which is the number of moles of nitric acid in the product, is equal to 5.88 kilomoles of NO2 coming from our converter gases, and this can be related to the amount of nitric acid by stoichiometry. Our conversion factor is 3 kilomoles of NO2 in the denominator is equivalent to 2 kilomoles of nitric acid in the numerator. Calculating, that is 5.88 times 2 divided by 3. Our answer is 3.92 kilomole HNO3. With this knowledge of the amount of nitric acid generated, we can then use this amount to determine the values of N2 and N4 coming from equations 1 and 2. Coming from equation 1, our N2 is simply 5.88 minus N3, 3.92. Our N2 is 1.96. This is kilomoles of nitrogen monoxide. Coming from equation number 2, we can rearrange this to solve for the value of N4 or the amount of water in the product stream. That would be 2 times 8.82 plus 50 divided by 18 times 2 minus the value of N3, 3.92. And this is divided by 2 to get N4. N4 is 9.64 kilomoles H2O. With these values determined, we can now answer the question, which is the composition of the absorber gas and the product stream. Let's start with the composition of the absorber gas. We only have two components, that is nitrogen and nitrogen monoxide. These are their kilomole values. So we have 38.71 and 1.96. Let's get the total, that is 40.67 kilomoles. And then from here, we can get their percents by mole. I'm choosing to represent this in terms of percent by mole because it's a gas mixture. And for gas mixtures, you can either use percent by mole or percent by volume. So for nitrogen gas, that is 38.71 divided by 40.67. That is 95.18% by mole. And for NO, that's 1.96 divided by 40.67. That's 4.82%. Alternatively, you can simply subtract 95.18 from 100 to get the percentage of NO in the absorber gases. For the last part of the problem, let's solve for the composition of the product stream. Now, the product stream needs to be represented in terms of percent by mass because it's a liquid solution. So we would have to convert the following moles for nitric acid and water to mass before solving for their percent by mass or percents by weight. So at the product stream, we again have two components, the nitric acid and the water. We have their mole values, 3.92 kilomoles and 9.64. Let's have their molecular weights. This is in kilograms per kilomole. So for water, molecular weight is 18. And for nitric acid, the molecular weight is 63 kilograms per kilomole. We simply multiply the molecular weights with the number of moles of the components to get the mass of the substances. This is in kilograms. So we have 63 times 3.92 for nitric acid. We have 246.96 kilograms. While for water, that's 18 times 9.64. 173.52 kilograms. The total mass, simply add 420.48 kilograms. And then from here, we can solve for its percent by mass. For nitric acid, that's 58.73% by weight. And for water, that is 41.27%. This is now the composition of our product. So what we have illustrated over the course of several problems is how do we solve a material balance problem involving the Ostwald process. From here, we can simply combine our learnings for the three different parts of the Ostwald process in order for us to perform a complete material balance on the entire process. You simply have to combine the oxidation chamber to the converter to the absorption column. That's the end of our lesson for stoichiometry involving nitrogen industries. Thank you for listening, and as always, keep safe.